Why does the universe look so empty? Yet galaxies seem designed like a massive web? If, after the Big Bang, the universe was almost uniform at the beginning, then where did these galactic walls, cosmic voids, and those enormous bubbles 1 billion light-years across, actually come from? Over the next 35 minutes, I'll take you to the very edge of the universe. When you look back, you'll see the largest structures in the cosmos. Were they designed? Or are they sounds frozen in time since the Big Bang? Actually, the first person to get close to this answer was Zeldovich. Even today, his fame among the general public in the West is nowhere near what his contributions deserve. But if we're going to talk about the largest structures in the universe, about those superwalls stretching across hundreds of millions of light-years, those super voids and galactic bubbles, there's no avoiding him. Zeldovich had already visualized the skeleton of the universe in his mind. He pondered a question. If the universe was nearly uniform at the start, then how did today's galaxies, galaxy clusters, and the cosmic web actually grow? This question would eventually lead us all the way to dark matter, the cosmic microwave background, baryon acoustic oscillations, dark energy, and even the ultimate fate of the universe. From the late 1970s to the early 80s, the way humanity viewed the universe began to change. Before then, to many astronomers, galaxies were just little smudges of light on photographic plates. Where they were, and roughly how many there were, of course, could be counted. But what scientists really wanted to know was, how are these galaxies actually distributed in three-dimensional space? If the universe has a structure, what exactly does that structure look like? In other words, they wanted to create a three-dimensional map of the universe. In this endeavor, two American astronomers were key. One was Margaret Geller, and the other was John Huchra. Their method, simply put, isn't that complicated. Measure the speed at which a vast number of galaxies are moving away from us. Because the universe is expanding. Generally speaking, the faster a galaxy is moving away from us, the farther away it is. By measuring the redshift of many galaxies, and mapping their positions and distances together, you can slowly piece together a three-dimensional map of the universe. But in practice, it's incredibly difficult. The light coming from distant galaxies is just too faint. Telescopes need a long time to collect those sparse photons. Dataset after dataset was measured, and patch after patch of the sky was filled in. Finally, the results began to emerge. The universe they saw wasn't just a random scattering of galaxies in the dark. It had a pattern. Galaxies were connected like thin filaments. This is what we call the cosmic web today. In 1989, Geller and Huchra announced an even more startling discovery. Deep in the universe, there was a massive structure made up of thousands upon thousands of galaxies, spanning hundreds of millions of light-years. It stretched across the cosmos like a wall. They called it the Great Wall. And that was only the beginning. Later, in 2003, the Sloan Digital Sky Survey discovered the Sloan Great Wall. It was even larger than the wall discovered earlier. Its scale is so vast that it reaches about 1/60th of the diameter of the observable universe. Then there's the South Pole Wall, which is closer to us. About 500 million light-years away, but just as staggering in length. Between these giant structures, the space isn't filled evenly with galaxies. On the contrary, in the gaps of the cosmic web, like the famous Boötes void, which is over 300 million light-years across, or the even larger Eridanus supervoid. These discoveries aren't just about mapping the universe. They forced us to face an even more fundamental question. What kind of force, over 13.8 billion years, sculpted the universe into what we see today? Long before these colossal structures were actually discovered, Zeldovich was already pondering this very question. He realized that the universe, right after the Big Bang, must have started out incredibly smooth. But it couldn't have been perfectly smooth. If the universe had been absolutely uniform at its birth, with not even the slightest difference in density, then today it would still just be a featureless ocean of matter. There would be no stars. And there wouldn't be any of us. So, the early universe must have had extremely tiny fluctuations. Much like an ocean that looks calm on the surface, yet hides very subtle ripples deep within. Zeldovich also understood that the only force capable of magnifying these tiny fluctuations had to be gravity, because gravity has a long enough reach. As long as one spot has a slightly higher density, it will attract even more matter. The more matter there is, the stronger the gravity becomes. The stronger the gravity, the more matter it pulls in. Over a vast amount of time, these initial differences, once so small they were barely visible, would be magnified into galaxies, galaxy clusters, filamentary structures, and finally, the cosmic web. The real universe wouldn't be that neat and orderly. When matter collapses, it won't happen perfectly the same way in all directions. 0.4, one direction will collapse first. As this direction contracts the fastest, matter will first be compressed into a massive, thin layer. Zeldovich called this image a pancake. Later, people came to call it the Zeldovich pancake. The name sounds a bit funny, but the meaning behind it is significant. It isn't necessarily just pretty spheres, but could instead be giant, sheet-like structures first. Subsequently, these sheet-like structures continue to collapse, intersecting to form filamentary structures. Where these filaments meet is where the density is highest, eventually giving rise to galaxy clusters. In other words, long before humanity actually saw the cosmic web, galaxies. Later on, computer simulations started to emerge. Scientists were finally able to test these ideas in a virtual universe. The results showed that Zeldovich's pancakes were just the first step. The universe isn't just a simple grid. It's a massive, ever-branching, intertwining, and interconnected web. And more importantly, the main character of this web isn't the stars we see with our naked eyes at all, but dark matter. In the latter half of the 20th century, the mass that truly dominates the universe isn't those glowing stars and nebulae. There is a vast amount of invisible stuff. It doesn't emit light, and it doesn't easily interact electromagnetically with ordinary matter, but it does have gravity. That is what we call dark matter. From the perspective of cosmic structure formation, dark matter is what builds the scaffolding first. It gathers under the influence of gravity, forming clumps, sheets, and filamentary structures. Ordinary matter, which is gas mainly composed of hydrogen and helium, just falls into these gravitational potential wells created by dark matter. But ordinary gas has an ability that dark matter lacks. It can collide. It can dissipate heat, and it can cool down. When gas gathers more and more in high-density regions, it eventually collapses. This all sounds quite grand, but the conclusion is actually a bit unsettling. When you look at a galaxy, even our own Milky Way, what you're seeing is only the glowing surface. Those stars, those beautiful spiral arms, are just a layer of frosting on a cosmic cake. What's really holding them together is the much larger, heavier, invisible halo of dark matter on the outside. The distribution of dark matter extends far beyond the visible edges of a galaxy, tethering individual galaxies into a larger cosmic web. By the end of the 20th century, cosmologists had formed a general framework for how galaxies are created. Galaxies didn't exist right from the very beginning. They slowly grew from seeds dating back to the early universe. The question is, where did those seeds themselves even come from? In 1989, a space telescope was launched into orbit. It was called COBE, or the Cosmic Background Explorer. Its mission was to observe the leftover glow from the very dawn of the universe. This glow is known as the cosmic microwave background radiation. It was first discovered in the 1960s. You can think of it as the cooling afterglow of the Big Bang. It has cooled down to just a few degrees. Yet it still fills the entire universe. The results from COBE were absolutely critical. It discovered that the cosmic microwave background is almost a perfect blackbody spectrum. This level of purity confirms that it truly originated from an incredibly hot and incredibly dense, early universe. This isn't just an ordinary clue. It is powerful evidence for the Big Bang model. But more importantly, it's the incredibly subtle ripples hidden within that afterglow. COBE detected temperature fluctuations on the order of 1 part in 100,000. It's as if, across the entire surface of the sky, there were extremely faint wrinkles, And these wrinkles are the seeds that eventually grew into galaxies and the cosmic web. The cosmic microwave background we see dates back to about 380,000 years after the Big Bang. The universe wasn't in its very first instant by then, but it was still incredibly young. So, the cosmic microwave background is like a photograph of the infant universe. Those tiny temperature differences within it are the first rough draft of the universe's structure. Over the next several billion years, gravity continuously amplified these tiny differences. Higher density regions grew into galaxy clusters, while lower density regions were hollowed out into voids. Little by little, the cosmic web took shape. However, this still doesn't explain everything, because within the cosmic microwave background, there isn't just random fluctuation. It also hides a larger scale, more structured pattern. To understand this pattern, we had to go back to before the cosmic microwave background was formed. Back then, the universe wasn't transparent yet. It was a hot, dense soup of plasma. Light, electrons, protons, and dark matter were all churning together in the same cosmic pot. In the early 1980s, there was a very special team of astronomers who started working on another cosmological mystery. They later became known as the Seven Samurai. They wanted to know just how fast is the universe expanding. This team measured the distances and velocities of hundreds of elliptical galaxies. They wanted to figure out where the galaxies in our local universe were actually moving and how fast. As it turned out, they discovered something strange. Galaxies aren't just following the expansion of the universe, moving smoothly away from each other. They're also being pulled by a massive source of gravity. In one particular direction, there seems to be a region with an incredibly huge amount of mass that's sucking a vast number of galaxies toward it. It isn't a single celestial object. It's not some supermassive black hole. And it's not one giant star. It's a vast region of space, containing a massive amount of galaxy clusters and dark matter. This discovery is important, because there is a fundamental assumption in cosmology. On a large enough scale, the universe should be uniform, and it should look about the same in every direction. But the Great Attractor tells us that even on a scale of hundreds of millions of light years, the distribution of matter is far from smooth. Gravity creates flows, and these flows also affect our measurements of how the universe is expanding. More than 40 years later, this line of research has led to even bigger discoveries. Researchers like Brent Tully from the University of Hawaii worked together to study an incredibly massive cosmic map. It's called Cosmic Flows 4. It contains over 50,000 galaxies. And it doesn't just tell you where the galaxies are, and also tell you how they move. And in this latest three-dimensional map of the universe, researchers have discovered something truly unexpected. Beyond the typical galaxy clusters and superclusters, there exists a massive, spherical shell-like structure. It is like a cosmic bubble outlined by galaxies, measuring about 1 billion light-years in diameter. It goes by the name of Ho'oleilana. The name originates from Hawaiian culture, roughly meaning sent murmurs of awakening from deep darkness. It is located over 800 million light-years away from the Milky Way. Structures like the previously discovered Great Wall, or even the Sloan Great Wall, all fall within its expanse. Its center also encompasses the Boötes Void. This raises a question. What kind of phenomenon could leave such a massive, circular mark on the universe? The answer takes us back to the early universe, back to the era contemplated by Zeldovich. Zeldovich understood early on that the universe following the Big Bang was not just a simple clump of matter. It was a hot, dense soup of light and matter mixed together. In the first few 100,000 years, the temperature was so high that electrons couldn't remain stable around atomic nuclei. So, ordinary matter didn't exist as neutral atoms, but rather as plasma. In this state, light and ordinary matter were tightly coupled, like a cosmic fluid oscillating in unison. Tiny density fluctuations were already present. Because dark matter doesn't interact much with light, it was able to cluster together first under the influence of gravity. The ordinary plasma also began falling toward these high-density regions. But unlike dark matter, the ordinary plasma contained light. That light generated radiation pressure. pushing the collapsing matter back outward. And so, a cosmic tug-of-war emerged in the early universe. Gravity trying to pull the matter inward. And radiation pressure pushing it back out. Pulling it in, then bouncing it back out. This constant oscillation created sound waves within the plasma of the early universe. These are the oldest sounds in the cosmos. Of course, this is not a sound that your ears could ever hear. Back then, there was no air, and no eardrums. There was no audience. What we call sound refers to density waves propagating through the fluid of the early universe. You can imagine it like throwing a stone into a pond. Ripples spread outward across the surface of the water. But in the early universe, it wasn't just one stone being thrown. It was more like a handful of gravel scattered into the pond all at once. Each little peak in density would trigger its own set of ripples. Countless circles of ripples overlapped and interfered with each other, forming a complex pattern. Then, the universe continued to expand and cool. About 380,000 years after the Big Bang, the temperature finally dropped to a critical point. Electrons could finally combine with protons, forming neutral hydrogen atoms. The strong coupling between light and matter was severed. The thick fog in the universe began to clear. Photons were finally free to travel through space. This was the moment the universe became transparent. The cosmic microwave background we see today is the light that was released at that very moment, and those sound waves from the early universe were frozen in place at that same instant. They no longer continued to propagate through the plasma as they once had. In other words, the cosmic microwave background isn't just an ordinary photograph. It also recorded that frozen moment of the early universe's sonic symphony. The tiny temperature variations later observed by COBE contained the imprints left behind by those oscillations. Where there were high-density peaks, it was easier for galaxies to form. Where there were low-density valleys, matter was pulled away, making it more likely to become a cosmic void later on. These frozen ripples were written into the cosmic web just like that. After billions of years, they are still preserved in the distribution of galaxies. This is what we call baryon acoustic oscillations. It sounds pretty technical, but the core idea isn't complex. It is simply a fossil left behind by the sound waves of the early universe. So, how do astronomers find this kind of fossil? In the distribution of galaxies today, they use a method called the correlation function. The name sounds intimidating, but the concept is very simple. You take a catalog of galaxies and then you start counting. How many galaxy pairs are separated by 1 million light-years? If we plot them out, we can see if there's a specific, preferred distance between galaxies. If galaxies in the universe were distributed completely at random, then this curve should be very smooth. There wouldn't be a sudden bump at any particular distance. But if the sound waves from the early universe really left an imprint, then at a specific distance, the number of galaxy pairs would be slightly higher. This curve would show a little bump. The scale corresponding to that bump is the furthest distance those sound waves could travel before the universe became transparent. This distance is called the acoustic horizon. It is essentially a standard ruler carved into the cosmic web. However, measuring this little bump is incredibly difficult. You can't just look at a few hundred galaxies. You need millions, even tens of millions of them. And for every galaxy, you need to know not just its direction in the sky, but also how far away it is from us. Otherwise, this signal will be completely drowned out by noise. So, humanity began conducting larger-scale sky surveys. The Sloan Digital Sky Survey in the United States is one of the most important ones. It maps vast stretches of the sky to measure galaxies. It doesn't just record their positions, it also measures their spectra to obtain redshift, which allows us to estimate their distance. On the other side of the Earth, Australia also has a complementary survey project. It's called the 2-Degree Field Galaxy Redshift Survey. It uses the Anglo-Australian Telescope at Siding Spring Observatory. This telescope has an aperture of 3.9 meters. Equipped with a special fiber optic instrument, it can collect light from up to 400 galaxies at once. This dramatically improved the efficiency of the survey. And so, Night after night, the telescope collected data, confirming the positions of galaxy after galaxy, and measuring their speeds. The most detailed three-dimensional map of the universe in human history began to slowly take shape. By the beginning of the 21st century, the results were finally in. The data from SDSS and the 2 Deci-Farads survey were both growing. Scientists began to measure the galaxy correlation function. The key question is, the frozen sound waves of the early universe, can they really be seen in today's cosmic web? The answer is yes. 2 research teams announced their results almost one after the other. In both the northern and southern skies, the same features appeared in the distribution of galaxies. There is a clear little peak in the correlation function. It is not random noise. It falls exactly where early universe physics predicted it would. In other words, scientists have truly found the fossils of those sound waves in today's galaxy distribution, an oscillation that occurred shortly after the birth of the universe, frozen for billions of years. In the end, we don't hear it as sound. Instead, we see it in the way galaxies are arranged. 20 years later, it is called Ho'oleilana. It is like a silent cosmic bubble, witnessing the remnants of that sound from the early universe. The scale of Ho'oleilana is hard to imagine. It is about 800 million light-years away from the Milky Way. Its diameter exceeds 1 billion light-years. If we rewind time to the moment the cosmic microwave background was formed, the scale it corresponded to was likely only a few 100,000 light-years. But as the universe expanded, this shell wall left behind by the early sound waves was stretched all the way to its massive size today. However, even if we understand how these sound waves formed, and how they were frozen into the cosmic web, there is still one problem left unsolved. Where did the initial fluctuations themselves come from? Why were there those first tiny irregularities in the early universe? Looking back even further, the answer is hidden in an earlier, more extreme era. This is where quantum theory and inflation theory need to take the stage. Science is sometimes very strange. When a theory is first proposed, maybe no one thinks it is important. Decades later, it suddenly becomes the key to understanding the universe. Black holes are exactly like that, dating back to the 18th century. But this matter was almost forgotten for nearly 200 years. Dark matter is the same way. There were early observational clues back in 1933, but it wasn't really taken seriously by cosmology until after the 1970s. So, to judge just how important a piece of work really is, it often takes a very long time. In the 1970s, 2 physicists, Timothy Bunch and Paul Davies, were studying quantum fields in curved spacetime. They weren't aiming for galaxies, nor were they aiming for the cosmic microwave background. They were doing purely theoretical mathematical research. But later on, to understand that, we first need to understand what quantum fluctuations are. You might start by picturing an electron. Many people imagine a little ball in their heads, carrying an electric charge, flying around an atomic nucleus. But the quantum world doesn't work that way. An electron is more like a probability wave. It describes what the probability is of finding an electron right here. So, what exactly is this wave rippling through? That brings us to quantum fields. You can imagine a quantum field as an ocean filling the entire space. A water surface can have ripples, and quantum fields can have ripples too. The only difference is that water is just in a pond, while quantum fields fill the entire universe. Electrons are ripples within the electron field. Quarks, neutrinos, and all sorts of fundamental particles can also be understood as excitations in their respective quantum fields. Looking at the most fundamental level, the universe is like many invisible quantum oceans layered on top of each other. Particles are simply waves on these oceans. Now, imagine a region of space with no electrons in it. You'd naturally think that since there are no electrons, the electron field should be perfectly calm. But quantum theory tells you that's impossible. Because the quantum world has uncertainty, a quantum field can never be completely at rest. It will constantly exhibit tiny fluctuations. Like a pot of water that can never be perfectly still, with tiny ripples continuously popping up on the surface. These fluctuations are known as quantum fluctuations. They are incredibly tiny. So small that they are usually impossible to detect directly. Unless, of course, something amplifies them. That is where inflation theory comes in. In the late 1970s, cosmologists were facing several deep, puzzling questions. Why is the universe so smooth on the largest scales? Why does space appear to be nearly flat, instead of being severely curved by gravity? Why don't we see them in the universe today? These problems were like cracks, appearing in the standard Big Bang model. Then, the question arose. Could it be that in the very earliest moments of the universe, space underwent an extremely brief and incredibly violent expansion? This is what we call inflation. It lasted for an unimaginably short time, on the order of 10 to the power of negative 32 seconds. But in that fraction of a second, which is almost impossible to fathom, space itself was stretched violently. The scale of the universe likely expanded by a factor of nearly 10 to the power of 30. This would have stretched space out to be extremely flat, and would have diluted certain strange relics until they were almost invisible. More importantly, it would have amplified those quantum fluctuations. The quantum jitters that originally existed only on a microscopic scale were forced to expand to cosmic proportions by inflation. When inflation ended, these quantum fluctuations were no longer just uncertainties in the microscopic world. They became real density variations. They were imprinted into the distribution of matter in the early universe. And then, gravity took over. Billions of years later, these initial ripples grew into galaxies, galaxy clusters, and the cosmic web. This is a truly mind-blowing connection. The Milky Way you see today, and those massive, hundreds of millions of light-years wide structures in the universe, if you trace them back to their origin, may have actually come from quantum fluctuations in the very first instant of the universe. Inflation transformed the microscopic into the macroscopic, turned uncertainty into cosmic structure, and took a slight tremor from the quantum world, turning it into the very backbone of our entire universe. Those tiny fluctuations in temperature within the cosmic microwave background, the fingerprints left behind by that very event. Later on, more precise observations, like those from the Planck satellite, mapped these fluctuations with increasing clarity. Inflation theory not only explains why these fluctuations exist, but it also predicts their statistical distribution across different scales. Like how many medium-scale versus small-scale fluctuations there are. Inflation models typically predict this number to be slightly less than 1. The results measured by the Planck satellite are around 0.96. And with very high precision. It bridged the gap between quantum physics at the smallest scales, and the structure of the universe at the largest. However, these discoveries aren't just here to satisfy our curiosity. The patterns left by the early universe also turned into a powerful tool. They help us measure how the universe expands, how dark energy acts upon it, and even where the universe might be heading. Now, when we talk about measuring the expansion of the universe, there is one name you simply cannot avoid: Edwin Hubble. Back in the 1920s, he used one of the world's largest telescopes at the time, the 100-inch Hooker telescope at Mount Wilson Observatory, to answer a truly fundamental question. Just how big is the universe? Many people back then believed that the Milky Way was the entire universe. Those faint, blurry patches of light in the night sky were likely just gas clouds within our own galaxy. But there were others who suspected that they might actually be island universes, independent galaxies distant beyond imagination. Hubble's observations finally put that debate to rest. He found Cepheid variable stars within those blurry patches. Cepheid variables are quite special. The period of their brightness variation has a definite relationship with their true intrinsic brightness. Once you measure their cycle of change, you can determine exactly how bright they really are. Then, by comparing that true brightness to the brightness we observe from here, Hubble proved that those so-called nebulae were actually far outside the Milky Way. They are independent galaxies, The universe suddenly felt so much bigger. Later on, astronomers kept refining their methods for measuring distance. Cepheid variable stars are great for measuring relatively nearby distances. For even further distances we have to rely on supernovae. Especially those supernovae with consistent and predictable brightness patterns. These celestial objects are known as standard candles. They act like rows of marker lamps deep within the cosmos, helping us measure distances billions of light years away. But astronomical distance measurement is never simple. Every method has its margin of error. And every layer of calibration could be hiding systematic biases. Scientists really need different methods to verify one another. That's where baryon acoustic oscillations become a very special kind of ruler. It's not a single star, and it's not just some galaxy. It is a massive ruler carved directly by the physics of the early universe. Since those early sound waves only had about 380,000 years to travel. As long as we know the physical conditions of the universe back then, we can calculate exactly how far those sound waves could have gone. This scale is what we call the sound horizon. It left its mark in the cosmic microwave background, and it also left traces in the distribution of galaxies later on. If you know how long this ruler was to begin with, and you can measure how large it appears across different cosmic eras, you can work backward to figure out how much the universe has expanded over time. This was supposed to be a truly elegant success, but it is precisely here that modern cosmology has run into a problem. The expansion rate derived from the early universe, that is, the cosmic microwave background, doesn't match the expansion rate measured using nearby galaxies, Cepheid variables and supernovae. Two methods, two different answers. This is what we call the Hubble tension. Measurements of the local universe show that the universe seems to be expanding faster today. As our observations have become more and more precise, this gap hasn't just naturally disappeared. Instead, it has become even harder to ignore. This has led cosmologists to start wondering, is there something missing in our understanding of the universe? Some believe that the Hubble tension might not be evidence of brand new physics. Perhaps there are still undiscovered systematic errors in our local distance measurements. After all, measuring astronomical distances has always been incredibly difficult. But some people also believe the problem might lie in our understanding of the early universe, dark energy or gravity itself. Could dark energy not be a constant? Are there perhaps additional particles in the universe? Could gravity have subtle deviations on large scales? These hypotheses are all very intriguing, but so far, none of them have been definitively confirmed. So, the Hubble tension remains one of the most important mysteries in modern cosmology. And baryon acoustic oscillations have another use as well. They can help us study dark energy. The method is quite elegant. The cosmic microwave background tells us what this standard ruler of the early universe looked like in terms of scale when it first formed. Modern galaxy surveys tell us what this ruler looks like after several billion years. At different redshifts. If the standard cosmological model is entirely correct, meaning that the universe contains ordinary matter, dark matter, and a type of dark energy that doesn't change over time, then the expansion of the universe should follow a very clear curve. The scale of baryon acoustic oscillations at different redshifts should also appear exactly as predicted. If the observations deviate from the predictions, then that could point to new physics. This brings us to DESI. DESI, which stands for the Dark Energy Spectroscopic Instrument, officially began operations around 2021. Years. The core capability of DESI is incredibly powerful. It has a robotic fiber optic positioning system that can precisely place 5,000 optical fibers on the telescope's focal plane, which are then fed into a spectrograph. In other words, it can measure the redshift of objects deep in the universe, in a nearly industrial, mass-production fashion. DESI plans to spend several years mapping tens of millions of galaxies and quasars. The map it creates isn't just a standard map of space. It's a map that contains information about time as well. Because the further away a celestial body is, the longer it takes for its light to reach us. So, looking further out effectively means looking further back in time. By using this map, which spans about 11 billion years of cosmic history, DAISY can measure the Baryon acoustic oscillation scale across multiple epochs. In other words, it uses this ruler left over from the early universe to track how dark energy has influenced the cosmos over time. In 2025, DAISY released new findings. This dataset includes over 1.4 million galaxies and quasars. Scientists extracted the Baryon acoustic oscillation signals from this data, and the results are incredibly clear. That frozen sound wave from the early universe is still etched into the structure of the cosmos today. But what's truly surprising is that, when reconstructing the history of cosmic expansion using these signals, the results don't seem to fit the simplest dark energy model. The data suggests that dark energy might not be a constant that never changes. It may have actually evolved over billions of years. Mind you, this isn't a final conclusion yet. It could become more significant as more data is collected. Or it could eventually fade back into statistical noise. But even so, it's enough to make cosmologists stop and take notice. Because if dark energy truly isn't a constant, the implications would be massive. In the Standard Model, dark energy acts like a gentle but persistent push, causing the expansion of the universe to constantly accelerate. If its strength changes over time, then the history of the universe becomes far more complex. Perhaps in the distant past, dark energy was weaker, giving gravity more time to dominate structure formation. Or perhaps it was once stronger, triggering a phase of additional acceleration even earlier on. Either way, it would affect the distribution of galaxies we see today. More dramatically, it would rewrite the fate of the universe. If dark energy keeps getting stronger, the universe could head toward a big rip. At that point, expansion would become uncontrollable, tearing apart galaxies first, then stellar systems and eventually, even atoms themselves. But if dark energy gradually weakens, the accelerated expansion of the universe might eventually stop. In some models, gravity could even take the upper hand again, causing the universe to eventually begin to contract. Of course, these aren't things we can draw conclusions about today. But they point to one thing: the vacuum might not be as simple as we once thought. Space itself, time, might not be an unchanging backdrop forever. What's even more interesting is that the hints of changing dark energy from DAISY and the Hubble tension might not be completely separate issues. If dark energy changes over time, then when we extrapolate from the early universe all the way to today, discrepancies might arise. This kind of discrepancy could be exactly related to the mismatch in expansion rates measured in the local universe. We can't say for sure yet that they are the same puzzle, but they are very likely two cracks in the same larger jigsaw puzzle. As the DAISY map continues to grow, and as more telescopes join in the measurements, we might discover that these anomalies are not just random noise, but signposts leading to deeper physics. Going back to the 1973 Warsaw Conference, Hawking back then probably would have found it hard to imagine what cosmology looks like today. Back then, cosmology was still very young. Many questions were supported only by a small amount of observation and a lot of speculation. But Zeldovich had already, from those limited clues, outlined the picture of how the universe's structure formed. Half a century has passed. We no longer just count hundreds or thousands of galaxies. We have started mapping tens of millions of them, drawing the skeleton of the universe out to billions of light years away. The tiny ripples in the early plasma have become the standard ruler of today's cosmology. Baryon acoustic oscillations are no longer just a theoretical term, but a tool for us to measure the expansion of the universe, test dark energy, and track the fate of the cosmos. We have seen signs that dark energy might be changing, and we are still debating the Hubble tension. And behind all these questions, you can still see that signature scientific intuition of Zeldovich. Don't just look at what's shining right in front of you. The true structure of the universe is often hidden in invisible gravity, hidden in the faint ripples of the early universe, and hidden within a vast, dark web spanning 13,800,000,000 years. From that fragile clearing of ideas at the Warsaw Conference, to today's DAISY robotic fiber optic arrays, humanity has come a long way. Yet the real questions have never actually changed. Where did the universe come from? Why did it turn out the way it is now? And, where is it ultimately heading? I'm Lao Ma, and I'll see you all in the next universe.